Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next several weeks, I will be releasing sample free response questions from each of the 4 AP Physics exams to help students familiarize themselves with what kinds of questions will be asked and how the AP Physics exams will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day, and this video series is primarily intended to help those students. According to AP Central, students can expect to see the following kinds of questions on the AP Physics 1 exam. There will be one on experimental design, one on qualitative to quantitative translation, one paragraph length response or paragraph argument, and then 2 short answer questions. The question in this video is type number 4, short answer. We will be taking a look at AP Physics 1 2017 free response question 3, which dealt with torque and conservation of angular momentum. The left end of a rod of length d and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot as shown below. Point C marks the center midpoint of the rod. The rod is initially motionless but is free to rotate around the pivot. Student will slide a disc of mass m disc toward the rod with velocity v0 perpendicular to the rod, and the disc will stick to the rod at distance x from the pivot. The student wants the rod disc system to end up with as much angular speed as possible. Part A. Suppose the rod is much more massive than the disc. To give the rod as much angular speed as possible, should the student make the disc hit the rod to the left of point C, at point C, or to the right of point C? Briefly explain your reasoning without manipulating equations. So on questions like this, which ask you to explain your reasoning, justify your answer, etc., after making some kind of selection, I recommend that you write out your reasoning or justification first and then make your selection, because you can't make a good selection until you've thought through the problem and the answer. And that's what this briefly explain your reasoning or justify your answer section is for. So we have a couple of ways we could think about this. One is that the disc exerts a greater torque on the rod when it pushes the rod farther from the pivot, or we can also think about it as the disc has greater angular momentum when it's farther from the pivot. The disc loses almost all its speed during the collision and hence gives the rod almost all its angular momentum. So the rod ends up with more angular momentum when the disc is farther from the pivot. In both cases, we need to select to the right of C. And then our scoring for this part, we're going to get a point for either one of these. There's my cursor. I lose it at least once every video, sometimes more than once. We're going to get a point for an explanation that the torque exerted by the disc or the angular momentum of the disc is greater when it's farther from the pivot. Part B, on the internet, A student finds the following equation for the post-collision angular speed omega of the rod in this situation. Omega equals m disk times x times v naught divided by I. Regardless of whether this equation for angular speed is correct, does it agree with your qualitative reasoning in part A? In other words, does this equation for omega have the expected dependence as reasoned in part A? Yes or no? Explain how you arrived at your answer. Again, I'm going to recommend that we explain first so that we can think it through, and then we will make our selection second. So here is our explanation. According to the equation, omega increases with x. A larger x produces a larger angular speed. And this agrees with my reasoning in part A, where I said a bigger x creates a bigger angular speed after the collision, so I would select yes. And then our points here are going to be for a selection consistent with the selection from part A, and notice that if you messed up in part A, but then kept the same kind of reasoning in part B, they only deem you once. And that's a really common way that the AP physics exams are scored. That if you propagate an answer into subsequent parts of the question, later parts of the question, and you had it wrong the first time, you're only penalized for that first mistake because you showed in the rest that you can use your answer correctly. And our second point is going to be really from this explanation down here, which is for indicating that the equation shows that omega increases with increasing x. And I am going to make this a little bit easier for myself. I'm just going to use the highlighter, guys, instead of writing, because look, according to the equation, maybe I will, I grabbed the eraser instead of highlighter. There we go. Sorry, happens sometimes. Instead of doing all that writing, according to the equation, omega increases with x. That's our second point. And there was a note that is also worth discussing for you, which is that if no is selected, the explanation may still earn full credit if an incorrect selection was made in part A. So if you messed up in A, but basically fixed it here by saying, oh no, this equation doesn't match, then you can still earn your credit for the explanation. Part C, another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with omega equals Ix v naught divided by m disk times d to the fourth. Without deriving the correct equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. Briefly explain your reasoning. So we've got a couple ways we can look at this. First of all, this equation says that if m disk is large, then we know that more angular momentum will be transferred during the collision. But this equation shows that the angular speed will decrease with an increasing m disk because it's in the denominator. We could also look at the fact that we know that if I, the rotational inertia is large, then there will be a smaller angular velocity as a result of the transfer of angular momentum. And the equation shows that angular speed will increase with increasing I because I is in the numerator. So your points here, let me make sure I have this. Okay, so your points here are, one, for focusing on the functional relationship or functional dependence of the variables, as opposed to, for example, the units or dimensions. Our second point is for addressing MDisk, I, or both. And I did it again. Lost track of my cursor. um, and then our third point is going to be for correctly concluding the equation is wrong because of the dependence on mass, disk, rotational inertia, or both. For parts D and E, do not assume that the rod is much more massive than the disk. Part D. Immediately before colliding with the rod, the disk's rotational inertia about the pivot is m disk x squared, and its angular momentum with respect to the pivot is m disk v naught x. Derive an equation for the post-collision angular speed omega of the rod. Express your answer in terms of d, m disk, I, x, v naught, and physical constants as appropriate. So, things that are cluing me into the approach that we want to take. We're talking about, oops, hang on, please. I'm going to highlight some stuff, but I want a different color. We're talking about like rotational inertia, angular momentum. We're asked about angular speed. So this is suggesting to me that we're going to talk about conservation of angular momentum. So our initial angular momentum of our system will be equal to the final angular momentum of our system. Prior to the collision, the disk has all of the angular momentum. And afterward, the disk and rod moving together have angular momentum, which we will be able to calculate with I of the system times their angular speed. Angular momentum of the disk prior to the collision was m disk v naught x. And then the rotational inertia of our system is going to be that of, let me just write one extra step in my algebra just to clarify, is going to be the rotational inertia of the disk plus the rotational inertia of the rod. So that will give us I for the whole system. So m disk v naught x will be equal to m disk x squared, because that was the value of the rotational inertia of the disk prior to the collision. And then plus I, because I with no subscripts is the symbol for the rotational inertia of the rod. And so now we can solve this for omega, which will be equal to m disk v naught times x, all divided by I plus m disk times x squared. And now for our scoring, we are going to have a point for using an expression of conservation of angular momentum for the disk and rod. Hold on, I lost. It happens multiple times, like every video that I manage to lose track, especially when it's orange and it's such a light color. But I only have so many colors I can work with, and I wanted to keep one that was consistent for scoring. So +1 for using an expression of conservation of angular momentum. Going to be a little lazy, save time. Ang mom for angular momentum for the disk and rod. Important note here, worth changing colors. Note, this point was not awarded for equating angular and linear momentum. They're not the same. Next point, for indicating the initial angular momentum of the system is equal to m disk v naught x. And then we're going to have a point for a dimensionally correct expression. So we really could start with this one. Dimensionally correct expression for the post-collision angular momentum. That includes I omega. So really, any one of the equations that included I omega for the final angular momentum would have been fine. And then our final point is going to come from indicating the correct rotational inertia of the system after the collision. Part E. Consider the collision for which your equation in part D was derived, except now suppose the disk bounces backward off the rod instead of sticking to the rod. Is the post-collision angular speed of the rod when the disk bounces off it greater than, less than, or equal to the post-collision angular speed of the rod when the disk sticks to it? Briefly explain your reasoning. So hey, if you've been watching my videos, you know how I do this. We're going to briefly explain first so that we can do all of our thinking, and then we'll come back up and make our selection second. So, the disk has a greater change in angular momentum during the bouncy collision when its angular momentum changes from the counterclockwise direction to the clockwise direction. To keep the system angular momentum constant, the magnitude of the rod's counterclockwise angular momentum must be greater than before, which means it has a greater angular speed. And so, points here are going to be for indicating. I'm going to use my highlighter again, guys, because it's just a little bit easier for indicating that the disk has a greater change in angular momentum during the bouncy collision. And you can do that directly or by analogy. And you can also think of this in terms of like an angular impulse. Even though that's not, an idea that's typically taught, that piece does translate over directly from linear momentum to think about an impulse. And note, and this is, again, worth that, pen tool first before I switch to highlighter. Note that this point is for describing what happens to the disk. And then our second point is for using conservation of momentum or momentum impulse reasoning to conclude that the rod gains more angular momentum and hence more angular speed in the bouncy scenario. So, again, I'm not going to write this all out, but basically, this whole second sentence is where this next point comes in, and I'll highlight it in a different color because it's for a different thought process, that we're talking about some conservation of angular momentum, talking about like the rod has more, which means it has a greater angular speed. Note that this point is for describing what happens to the rod. So we had 2 points here, 1 point for describing what happens to each of the two objects involved in this interaction. Let's clean that up, make it a little bit more legible. Okay. I hope you have found this demonstration of an AP Physics 1 free response question helpful. If you have a video solution you'd like to request from my YouTube channel, you can send it to physicsproblemrequests@gmail.com. If you need some email assistance, you can send it to freephysicshelpline@gmail.com. Send your question and the work you've done on it, and there's a limit of 10 questions per academic year for that free help. If you'd like to know more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics 1 exam. And those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.